Alright, gang, here we go. This is for Chem 2, Unit 8. We're talking about liquids and intermolecular forces. Later on in the unit, we'll talk about solutions, concentrations, so on and so forth. Alright, so to start off the unit, once again, we're going to go back, touch some basics real quick, just to make sure we're all on the same page, and then moving forward, we'll start covering a little bit of new stuff. So intermolecular forces, from Chem 1, you should be familiar with this idea of intermolecular forces. They're defined as attractions that occur between your molecules. Okay, so these are the things, so like they've got two hydrochloric acid molecules, hydrogen chloride molecules here shown, and they've got this bond here that's attaching the hydrogen and the chlorine. Those are known as intramolecular forces. Okay, essentially these are what makes up our bonds, and we've talked a lot about bonds. We've talked about ionic and covalent, metallic bonds. Okay, and so these are known as intramolecular forces. All right, intramolecular, and then the forces that attract two different molecules together are known as intermolecular forces. All right, or intermolecular attractions. All right. So intramolecular forces, pretty much, they tell you what the chemical properties are going to be. All right, chemical properties. And then the intermolecular forces, well, they tell you the physical properties. Okay. All right, and we'll talk about more of these as we move on, as we talk about these intermolecular forces. But like boiling points, melting points, viscosity, surface tension, capillary action, these are the ones that we're going to focus on. But really, any physical property is pretty much determined by the intermolecular forces. Now, there's a little bit of overlap in some cases, but for the most part, physical forces or physical properties are determined by the intermolecular forces. All right, states of matter should be really clear on these ideas now. Okay, but essentially the fundamental difference, what causes these different properties of these states of matter, are the intermolecular forces. Gases generally have really, really weak intermolecular forces, and this is what allows them to spread very far apart from one another. So there's a lot more kinetic energy to the particles compared to the intermolecular forces. And then liquids, that difference becomes a lot less. You've got the forces are keeping them much closer together. And so they're stuck together. So like in these bromine molecules they show here, it makes a liquid. They can still move past each other, so they're not super strong. The kinetic energy keeps them moving past each other, but they have to stay relatively close to one another. And then finally, in the solids, they are stuck in a crystalline structure, and the intermolecular forces are really holding them together compared to the intermolecular forces. All right. So, and then one thing to remember is whenever we talk about temperature, we're really talking about the measure. It's a measure of the average kinetic energy. Okay, so, and these two values are proportional to one another. So as our temperature goes up, the average kinetic energy of our molecules is also going up. Okay, general properties of states of matter. Go ahead and pause and just take a glance at these. There's nothing new here. Especially we just spent an entire unit talking about gases, and we've done liquids and solids. Should be pretty easy. All right, relative strengths of attraction. So this is just showing you intermolecular forces versus intramolecular forces. So these guys here, these are your intramolecular forces. All right, and notice that their melting points and boiling points are really, really high. This implies that they have very, very strong things that are keeping them together. All right, intermolecular forces primarily affect, as when you're talking about melting and boiling, the intermolecular forces define the molecular compounds, or the covalent compounds. So you got nitrogen, hydrogen chloride, and hydrogen fluoride. Notice their melting boiling points are a lot lower than these guys up here, where they were determined by the intramolecular forces, where you had covalent bonds, ionic bonds, and metallic bonds holding them together. All right. So in general, it's pretty easy to see that intermolecular forces are a lot weaker than intramolecular forces. All right. So, and then there's one trick here later on when we talk about intermolecular forces, and hopefully you learned this in Chem 1, but just to recover it real quick, hydrogen bonds, okay, is the strongest intermolecular force. All right, but notice that we use the term bond for it, but that it is not a chemical bond. It's just, we use the term bond as kind of it's a misnomer. Okay, it's telling us like, oh, it's a bond, but it's not. But it's only a bond in respect to the fact that it's much stronger than the other forces that are participating in our molecule. All right. So types of intermolecular forces between neutral molecules. All right. So that when we say neutral, whoa, okay. Where'd I go? My dogs are going nuts. Can you hear them? All right. So between neutral molecules, so weakest, strongest. So when we say neutral, okay, essentially what we're saying is that they do not have charges. So they're not ions. Okay. All right, but they can have a dipole. They can be polar. Neutral molecules can still be polar. They just don't have an overall charge. All right, so don't let that confuse you. All right, weakest to strongest. All right, dispersion forces are the weakest force. All right, they could also be referred to as London dispersion forces. All right, or induced dipole interactions. All right, so for the most part, I'll refer to them as either London dispersion or just dispersion forces. These are the weakest forces. We'll talk about how they occur here in a second. And then dipole. All right, and these are between molecules that have polarity or dipoles on them. And then hydrogen bonding, which is really just essentially a special dipole force. All right, and then you could also you might hear in other chemistry classes this idea of van der Waals forces. Van der Waals forces are these two things combined. Both of these guys combined are the van der Waals forces. All right, so dispersion forces. Okay, it can occur to any molecule, and essentially what happens is you have a nonpolar particle, and they're using helium as their example here. Okay. And then they can be temporarily polarized to create dispersion forces. All right, so let's show what this kind of looks like. All right, so imagine that you've got your helium atom right here, and remember the electrons are kind of, they're bounced around, and they have like this area around the atom that they're most likely to exist. Right, and so we'll just draw two of them right now. But you could imagine that if we have a clump of helium, like there's billions and billions of these, but we're just going to show two of them. Okay, and so these electrons, these are the electron clouds. So these are the highest probable locations that these electrons will be around these helium atoms. Now, what can happen, and now remember, there's billions and billions of these guys, and in the vast majority of cases, these electrons are going to be far apart from one another because they're both negatively charged. They're going to repulse each other, right? So because they're like charged, okay? And so for the most part, they'll be far apart from one another. But because there's billions and billions of them, and there's it's really a numbers game. You can have a probability. There's your nucleus. What could happen is both of your electrons, okay, could just for a fraction of a second locate themselves on one side of your atom versus the other. And so really, if we were going to draw a circle for the electron density at that instant, it would look something like this. Our electron density would look like this, right? And so there's your electron density. So what this happened is this is essentially now a positive end, right? So this would be, give your little delta plus, your partial positive side on that proton there. And then on this side here, you'd have your negative. So there's your partial negative charge, your delta. And so you get like the instantaneous polarity of whatever atom you're talking about. In this case, we're using helium as our example because it's kind of the simplest, all right? Because it's the smallest single atom particle. Anyway, and so you've got a positive, negative. And now think about this for a second. Well, what would this do to the surrounding heliums? Remember, these guys, there's billions of them, so and whatever one does, it affects the one around them. Okay, so what would this do to this other one? Right now, they're both neutral, but you could imagine, like, well, if this other helium atom is right here, this negative charge from this guy, because it suddenly becomes negatively charged, well, it's going to push those electrons away. So instead of the electrons being on opposite sides of this atom, it'll push them away. So they'll be like this as well. And so what this does is this will push the electrons, and then we'll have something like that for the electron density. And then it'll put an induced dipole. Oops. It'll put an induced dipole on the other side as well. And that's really why we call them induced dipoles, is because it's a dipole, but the dipole is not naturally occurring. It's being induced on whatever molecule or atom that you're looking at. Okay, and so you can imagine that just by pure numbers, statistically, this will happen, because you got billions and billions of these particles. And so when one of them gets that flip switch, so it gets a positive and a negative, it's going to create almost like a domino effect to other molecules or other atoms that are around it. So those other atoms will end up get an induced dipole in them that'll last for half fraction of the second, and it'll just kind of get passed around. And because it's got this induced dipole, it creates this general attractiveness between these molecules. But because it lasts only a fraction of seconds, that's why we define it as ridiculously weak. All right, so what we really care about, and now this happens to everything because everything has an electron cloud, okay? But what's important to be able to do is determine, well, how much would that dispersion force happen? Okay, so different molecules have different abilities to be distorted, or their electron clouds have different abilities to be distorted, and we call that polarizability. So essentially, it's just how easy is it to make it polarized, have a positive end and a negative end. How easy is it to induce that dipole is essentially what we're looking at. All right, so here's a list of some things that we look at when we're trying to determine the strength of dispersion force or the ability to polarize. The dispersion force increases as the polarizability increases. Okay, so the number of electrons in an atom, okay, that tends to make you have really, really big clouds. So you imagine having a pillow that's got a lot of extra feathers in it. That sucker's really squishy, okay, because it's got a lot of extra feathers in it. And so you can imagine that an atom is kind of the same way. It's got all these extra electrons in it before you get to that hard nucleus right in the middle. And so it's really easy to squash that pillow down. Right, and you can distort that pillow really easy from one way to the other. Imagine like a beanbag chair that's, versus like a chair made out of a rubber ball, right, or something like that. Okay, and so this chair or this pillow can be squashed just like your nucleus. So the number of electrons in the atom gives it more polarizability. Okay, meaning these electrons, it's more likely that one of them, that they'll be all on one side versus the other side of your atom. Okay, so the more polarizability, the more squishy it is, the more polarizability it has, and so therefore the more dispersion force it has on it. Okay, the size of the atom or molecule, or the molecular weight, also affects it. Okay, the bigger it is, the more dispersion forces it has. All right. And so essentially, like, it is the same idea as the first one. The bigger it is, the easier it is to squash it, the easier it is, or the more likely it is for the electrons to be on one side versus the other. Okay, and generally just the size of the atom, as your atom gets bigger, it gets more electrons. So number one and number two generally go hand in hand. I mean, it's two sides of the same coin. Okay, number three, shape of the molecules with similar masses. So if you have two molecules that have similar masses, so here we've got N-pentane, C5H12, and it's completely linear, right? Our carbon molecules go 1, 2, 3, 4, 5, like that. And so it's a completely linear molecule versus neopentane is kind of a spherical molecule. Okay, so it's got a carbon in the middle, and then the carbons jumping out on either side like a tetrahedral. And then off of those, you got your three hydrogens off of each of those carbons. But anyway, they've both got the same number of carbons and hydrogens, so they have the same mass. Now notice that this molecule here is a lot more spherical. It has a lot less surface area, and it's a lot more compact. Okay, and because it's more compact, it has less polarizability, and because it has less polarizability, it has less dispersion forces, as opposed to N-pentane, it's just this chain. Okay, and the electron clouds are spread out evenly around it, and so it's got increased surface area because it's no longer a sphere, and so therefore it's more polarizable. All right, and we can see something trend here. Okay, so if it's harder to polarize, it has a lower boiling point. Okay, if it's harder to polarize, it has a lower boiling point, because that's its intermolecular forces are weaker. Okay, so it's easier to boil. All right, so like neon is harder to polarize. Okay, and so therefore it boils at a much lower temperature. And the way it's worded is kind of confusing, right? Or maybe it's just the way my brain's working right now. And then fluorine is much easier to polarize, so it's got higher dispersion forces, so it takes much more energy to make it boil. Okay, and so this is you can see this trend going, and you can compare all these different things. I think it's interesting that sometimes it shows these these intermolecular force, or you're showing halogens versus these noble gases, and you can see how the halogens come in pairs, right? They're diatomic, and so they're automatically they weigh more, right? because there's two of them, like fluorine, difluoride, right? Two of them would weigh about, what, 38 grams per mole or something like that, and neon is about 20, right? So, and then the fact that neon is essentially a sphere and fluorine is two spheres that are butted together. Okay. Next intermolecular force here, we've got dipole-dipole interactions. All right, and so polar molecules. So remember back several units ago now we talked about Lewis structures and how to determine whether or not your molecule is polar. Okay, and we use these symbols to determine if it's polar, right? It had a delta positive, delta negative. Okay, and so essentially these guys are acting kind of like magnets, and they attract one another. So oppositely charged ends are attracted to one another. All right, so they kind of have this interesting thing here. So they've got this molecule CH3CN. Okay, and it's a polar molecule. On the nitrogen end, it's got extra lone pairs. Okay, so that's negatively charged. Okay, and then on the positive end is the CH3, this little methyl group hanging off of here. And then these guys here, the negative end of the nitrogen are attached to the positive end of the CH3. And so you get this attraction that's occurring. And notice that when it's a solid right here, it's primarily determined based off all of these. You get this nice little crystalline structure. Okay, you get this 1, 2, 3, 4-sided shapes, kind of pretty much appearing just very regularly. All right. But then once you start adding in extra kinetic energy, these guys start moving around a little bit more, and so notice that they start orienting themselves less perfectly. Okay, and as they orient themselves less perfectly, you start getting repulsive forces as well. So look, these nitrogen groups are really close to one another, so you get a negative on negative end, so you got repulsive forces occurring at the same time. And so because of that, your kinetic energy is overcoming some of those intermolecular forces, and so these molecules are able to move past each other more frequently. All right, so therefore it's a liquid. Okay. So, I mean, generally the trend is pretty obvious here. If you're looking at molecules that have essentially the same molar mass, so you've got propane, dimethyl ether, acetaldehyde, and acetonitrile. That's the one we just looked at the other slide there, acetonitrile. Okay, they have essentially the same molar mass, 44, 46, 44, and 41. It's pretty dang close. Okay, but notice that their boiling points are increasing steadily as their dipole is increasing. So remember, this mu factor here tells us what the polarity is of our molecule. All right, and we measure it in these D's. Okay, and so these guys are showing us that as the dipole value increases, the boiling point is increasing as well. Okay, so notice acetonitrile, even though it's the lightest, and it's arguably the most compact, right? It's still got the highest boiling point, and that's because it's got a lot more dipole. So even though if you were just comparing its dispersion forces, the dispersion force would tell you that it has the weakest dispersion force, but because of this polarity, it's actually got the highest value of intermolecular forces acting on it. Okay, now, so that brings us to an interesting question. Okay, in Chem 1, we just pretty much told you dispersion forces, London dispersion force is always the weakest, period, don't worry about it. Dipole force is always stronger. The fact of the matter is the different things, you can actually, they kind of have an overlap zone that you can have sometimes where your dipole is actually weaker than your dispersion force, and you have to be able to distinguish when that might happen. Okay, so here are two general rules to help us. Okay, if two molecules are of comparable size and shape, their dipole-dipole interactions will likely be the dominating force. So like these guys here, they're pretty much the same size, and I mean they're pretty close to the same shape. They're all kind of like this linear, like almost like a short hot dog kind of shape is kind of how I view it. All right, or like a little sausage link shape. Okay, and so they're all generally shaped the same, and they have the same molar mass. So their boiling point is determined by their polarity. Okay. However, if one molecule is much larger than another, so like a factor of like 5 or 10, okay, then the dispersion forces will likely determine its physical properties. So if you're going to compare acetonitrile to something like dodecane, which is a 12-carbon chain, the dodecane would most likely have a higher boiling point than acetonitrile, even though it's not polar, okay, because it has a much bigger dispersion force. Okay, and so this graph is kind of interesting. It kind of allows us to look at these different trends be able to get an idea of their intermolecular forces based off their boiling points as different things change. All right, and so you got your molecular weight down here and your boiling point in your y-axis. Okay, and so group 4A, so this is the group that has carbon, silicon, etc., and they're just simply pairing these guys up to fill out their octet with hydrogens. And you can notice that as you go down the group for this guy here, all right, for carbon to silicon, germanium, and tin, that your boiling point steadily increases. And that makes sense because it's a nonpolar molecule, right? It's a nonpolar molecule, but and so as it gets bigger, it gets fatter and more squishy, more polarizable, and so therefore your intermolecular forces go up and the boiling point goes up. All right, but then the other three interesting things happen, right? So you can see that for the first three, or the last three groups here, so let's look at the next one, group 5A. So this is nitrogen, and then this guy here would be phosphorus, and then arsenic would be right here, and then we have antimony right here. And you can see that for these three, it follows the exact same trends. All right, as you go down the group from phosphorus, arsenic, and antimony, okay, you go up in boiling point because they're getting more squishy. But notice that they have the opposite trend from the period 2 as you look to period 3. Okay, from the nitrogen to the phosphorus. Nitrogen has a significantly higher boiling point, or versus the phosphorus group does. Okay, in fact, the nitrogen is almost as big of a boiling point as the antimony. Okay, and then you can also see as we look at group 6 and 7. 4, 5, yep, 6 and 7, that you can see the same thing. Water has an absurdly high boiling point. Okay, even more so than hydrogen, even though hydrogen fluoride is much more massive than water. Okay, and so it's like, well, what's going on? These guys are our outliers. What the heck is going on with these guys? So this leads us to our last intermolecular force here. Okay, and so it brings us to, well, not our last, but the last one for a second. How about that? Brings us to hydrogen bonding, right? And so you learned all about hydrogen bonding in Chem 1, and it's a special case of dipole-dipole interactions, and it's experienced when you have a hydrogen bonded to NO or F, okay? And I remember it backwards of this as F, O, or N, because hydrogen bonding is fun, and fun is spelled F-O-N. Okay, that's how I remember it. So specifically, you need two things. You need a hydrogen, and it needs to be bonded to fluorine, oxygen, or nitrogen. Okay, and that's when we can have hydrogen bonds. Okay, now remember, it's labeled bond, but it's a misnomer. It's really not a bond, right? It's just a really strong intermolecular force. Still not nearly as strong as an actual covalent or ionic bond or metallic bond, but it's really strong compared to other intermolecular forces. All right, and so what happens is that, like here, because oxygen is so much more electronegative than hydrogen, it's going to jack all the electrons from the hydrogen. And so right here on this hydrogen, you essentially have just a point charge, just a positive proton just kind of out there floating that's essentially negative all electrons. And so you got this pure positive charge and then a very dense negative charge here. Okay. And so you get this intermolecular force, and we call this the hydrogen bond between the naked hydrogen and the electron-rich oxygen. Okay, so you get, it's just a dipole, but it's a really special, strong one. Okay, and so you can see that in Chem 1, we primarily focused on like these groups, like, well, would it experience hydrogen bonding to itself? Okay, and then but now we want to be able to also identify, well, can you have hydrogen bonding to something else? So notice that we can actually have between ammonia and water, you can have hydrogen bonding here. This explains why ammonia is ridiculously soluble in water, and we'll get to that later. Okay, so it's just about this. And we just talked about this slide. Okay, it's the atoms interacting with nearly bare hydrogen nucleus and then being pulled towards the electron-rich, electronegative atom, nitrogen, oxygen, or fluorine. So this explains lots of interesting things, and especially water. Okay, it explains a lot of really interesting characteristics of water, one of which is the fact that as water freezes, it gets less dense, and it's because it forms these really nice hexagonal structures, because the oxygen molecule has 2 electron pairs and then the hydrogen bond, and so the hydrogen bond can be bonded towards these lone pairs that are sitting here, and then so as it freezes, they move farther apart to form this crystalline structure, whereas when they're liquids, they're really close together to one another. Okay. So let's do a couple practice problems and we'll call it a day. How about that? All right. So which of the following substances is most likely to be a liquid at room temperature? Well, remember, liquid is going to occur when we have high intermolecular forces. So the ones that have the highest intermolecular forces are the ones that we're going to have the highest or the most likely chance of being a liquid at room temperature. Okay, so really, let's just go through it and try to figure out if we can figure out which of these molecules would have hydrogen bonds, because the one that has hydrogen bonds is going to be the one that has strongest, because that's the strongest we've talked about so far. So now, you got to be careful, okay? So, like, you're looking at formaldehyde right here, and you're probably thinking to yourself, oh, this could have hydrogen bonds because I got hydrogen and I got oxygen. Well, remember, specifically, the hydrogen needs to be bonded to the oxygen. And in formaldehyde, the carbon is the middle atom, right? So you got to brush off your Lewis structures, okay? And so formaldehyde actually looks like this. The carbon with two hydrogens attached to one another. This is your formaldehyde right here. And so you can see that this hydrogen is not attached to this oxygen. So this guy cannot have cannot have hydrogen bonds. All right. Fluoromethane. Okay. Oh, well, now you're looking at it. Oh, the hydrogen fluorine. Sure enough, hydrogen bonds. Not quite. Which one's going to be the middle bond? You can't, or the middle atom. You can't have hydrogen in the middle because it can make one bond. Fluorine is stupidly electronegative, so it's only going to make one bond. It's not going to share any of its extra electrons. All right, so the carbon is going to be in the middle again, and it looks something like this. All right, so again, right, and you got lone pairs around the fluorine. And so again, even though there's hydrogens and a fluorine, okay, these hydrogens are not connected to this fluorine, so you cannot have intermolecular forces here. All right, and the same thing happens with hydrogen cyanide. Carbon is in the middle, okay, but hydrogen peroxide here, well, if we draw out hydrogen peroxide, all right, it looks like this. All right, so you get lone pairs around the oxygens. Okay, and so notice that now, yes, in fact, we do have these bonds, these hydrogens bonded to the oxygen, and so you can get this hydrogen bonding between these guys. All right, and you should recognize the fact that hydrogen peroxide is in fact a liquid at room temperature. All right, and then hydrogen sulfide, well, this isn't, you can't have hydrogen bonds at all because sulfur is not fun, right? Okay, let's see, what's this question? All right, yeah, so this is essentially just the same thing. When you're solving this, okay, make sure you're checking for your Lewis structures, okay? Let's see, just a spoiler alert, only one of those is capable of having intermolecular force, or having hydrogen bond. Okay, last intermolecular force we'll talk about here is ion-dipole interactions, all right? And this is essentially what allows ionic compounds to dissolve in polar solvents like water. And so remember, so you've got sodium and chloride. So as our example, like if you've got sodium and chlorine, they'll form an ionic bond together. And essentially that ionic bond is that electrostatic attraction, the fact that the sodium is positive and the chlorine is negative. And so the positive and negative are going to attract one another. All right, and so what essentially happens is this water molecule that's polar is going to surround the positive and negative, okay, and it's going to interrupt that force, that bond that's attracting these two together, okay, and so you get this ion-dipole interaction, all right, so it's another intermolecular force, and it's a very strong, all right. So here's a nice little chart that helps you figure out what intermolecular forces are going to be present when. All right, so this top column is your dispersion forces. Notice that every single type of molecule is going to have dispersion forces. Dipole molecule or dipole-dipole interactions can only occur when you have polar molecules. Okay. All right, and then hydrogen bonding occurs when you have a polar molecule, but it has to have OH, NH, or HF. Okay, and then ionic dipole, you need an ionic solid dissolved in polar liquids. All right, and so the strongest force is the one that's going to dictate the extent of the attractions. Okay, so when you're looking at it, you got to decide, all right, which is the strongest force that's affecting this molecule? And so remember, we talked about specifically, they generally go in this order: dispersion dipole, hydrogen bonding, ion dipole. But there's also, there's this fine line between these two here, between dispersion forces and the dipole-dipole interactions, where you have to be able to figure out, well, which one's actually stronger, et cetera, et cetera. All right. And so this kind of just walks us through one more little bit about being able to figure out strength of intermolecular forces. Okay, so here's our two basic rules. When two molecules have comparable molar masses and shapes, dispersion forces are roughly equal to one another. Okay, and then when two molecules have very different molar masses and there are no hydrogen bonding, dispersion forces determines the substance with the stronger attraction. Okay, so there's your two rules to figuring this guy out. So let's do one of these. Okay. So this problem is actually really easy, but we'll take a gander at it anyway. It says list the substance, these guys here, in order of increasing strength of intermolecular attractions. All right, so we'll just start with the strongest and go down to the weakest. So our strongest force was ion dipole, right? None of these guys are ionic compounds, so that one's right out. Next one was hydrogen bonding. Okay, so which of these could exhibit hydrogen bonding? Well, the only one that could exhibit hydrogen bonding is this guy, acetic acid. Okay, so he has to be the strongest. So it's either C or E. All right, either of these would have to be the strongest, or have to be the right answer, because he's going to have the strongest intermolecular forces. All right, then we have to look at dipole-dipole interactions. Well, argon can't have dipole-dipole because this is essentially just a sphere. Chlorine, well, you got one chlorine attached to another chlorine, so he's not going to have any, right? He just looks like this, chlorine to chlorine. These don't have different electronegativities, so you can't have a polarity between those two guys. And then methane, well, he's going to be nonpolar because it's a tetrahedral shape, all hydrogen surrounding it, so he's nonpolar as well. So then the next one is we got to look at our dispersion forces. All right, so dispersion forces, remember, we're looking at squishiness of the molecule, okay, versus size of it, mass of it, etc. Okay, so argon, all right, remember argon is just this lone noble gas right here, okay, and he's going to have the weakest intermolecular force, even though he's going to weigh the second most. Chlorine weighs the most out of all of these, right, because he weighs about 70, argon weighs about 40, and methane weighs about 12 plus 6, so 16. 12 plus 4 is 16. Okay, so argon's going to be the weakest because of the fact that he's not spread out at all. Okay, and so really we're just narrowing it down between C and D, and so E has to be our right answer. All right. Okay, go ahead and work these out on your own. You're identifying intermolecular attractions present in the following. Okay, and then select the one with the highest boiling point, and that's going to be the one with the lowest, or that's going to be the one with the most, or the highest intermolecular force acting on it. All right, and so that's it for this video. Pretty long one, lots of stuff to learn, new things, lots of review. Do your homework problems. Let me know if you have any questions, and I'll see you on the flip side.